Hello everybody, I welcome you to our KiCad tool training part 2 out of 2. This part covers the Layout Editor and Gerber viewer, and it's based on KiCad version 8.0. Before we start, I want to motivate our KiCad tool training for today about layout tasks and its working steps. So what we did is we entered the left schematic into our KiCad program. And now we have to do the following. We have to discuss layout constraints, mechanical aspects, we have to do the routing, and we have to prepare our data for production. So these are the 4 major steps we have to do in order to produce our PCB. If we have a little bit a closer look, we will cover the following working steps. First, update your schematic, maybe something has changed. Clarify PCB constraints. This is divided into 2 questions. The first question is your own constraints. So this means in our case, for example, board size, we define it's 52 millimeters by 25 millimeters. For mounting holes, we take M3 screws. We say we take a 2 copper layer board, so top layer and bottom layer. And we can assign to the top layer, in our case, a signal routing, and to the bottom layer, the ground plane. So these are the layout constraints that's coming from our side, maybe depending on which case you are going to use or where you want to fix your board. The manufacturer's constraints are coming from the side, what distances you have to take between traces, what's the minimum width of a trace, etc. So these are the 2 constraints which have to be clarified before you start layouting, especially before you start routing. Otherwise, maybe you make a nice looking board, but it cannot be produced because you drive the constraints of your manufacturer. So this is what we did. Board dimensions, mounting holes, this is coming from your project, as I mentioned. Then we have to perform the routing. So this means importing your net lists and some fly lines to place the components on your board. Then we have to resolve crossings. If you have crossing traces, you have to think about how to tackle this. We perform the routing. We have to make filling area. This means the areas where you don't have traces can be edged away completely, but this is very expensive. That's why you put copper islands, and on the one side, it's a coast point. On the other side, if you have these islands, you also can put them to ground or power supply. So you get some shielding of your signals. So we will make this filling areas. We had to put project information on the top silk layer. This means you have to add the project name, revision number of your board. In our case, also the group name and student numbers. We perform a design rule check. This means we can automatically check if we hold the constraints we entered upfront to our PCB layout and the board is producibility. Then we will export the Gerber files and we will use the Gerber viewer to check our Gerber files, and finally we transmit the Gerber files to our manufacturer. Once we have talked now about layout task and its working steps, we start over with updating your schematic. If we look at our schematic, which is shown on the left side, we have to think about what is changed, the first question. In our case, we can say nothing changed, so no change of component, no change of currents, whatever. The next question we have to ask before we go to layouting is what's about testing. This seems to be a very interesting or a simple question, but indeed it's very important, because before you start layouting and routing, especially, you have to think about what signals do you want to test later. This might be taking just a multimeter to check a voltage. This means also to take an oscilloscope to check a signal, or if you want to have digital data where you can put the logical analyzer to trace or to capture, for example, I2C bus or SPI or even the MIPI bus or USB bus. So this must be put into the account now, because otherwise you miss to enter the test points on your board. So that's the one thing. And then we have to think about assembling. Maybe it makes sense to put some assembling nodes here, and also layout constraints. For example, you can put here a window with a text where you say which is the board size, the screws used, and etc. So that's what we are going to do now in our schematic editor. So now we see our schematic. As we said, we have nothing to change regarding the components, but we want to add some test points. What's interesting to test, of course, is our output signal. So we want to add a test point, add component here. And we can search for test point. We'll get a test point. With no footprint, we have to assign this later on. We'll assign it shortly. So at the output, one test point. The other test point, which is interesting in this case, might be the voltage, but this is the supply voltage, but this is not so an issue. It is very simple circuit. But what might be interesting is to see the charging and discharging of our capacitor. So we also test, for example, our threshold or input voltage to our comparator. So we put a test point here too. And wire it. And here we have already wired it. And we can give him useful names. Right click, properties, value test point. It's maybe too easy. We can take it out. It's clear it's the output of our circuit. And here we can put, for example, TR or THR. No properties, no cancel. Sorry, we take test point. It's whole. Go to properties and put here TR. So this are assigning the test points. We can save our schematic. One thing now is we have to add our footprint. So we go to the footprint assignment tool again. We see the assign stuff, and we see here our new test points out in TR. Personally, you have here also a library for test points. You can use one of them, but what I like is to take just a 2.54 millimeter pin header and to assign here the vertical pin 1, 2. Let's have a look how it's looking. View the footprint. It's showing like this. It's looking like this. If you look 3D, it's just such a simple pin which you can add on your board. So we assign this footprints. Footprint editor can be closed. Save, of course, we have some changes. Okay, and we put here full screen. Then, as we said, we can make some annotations about layouting. You can, for example, put here sensitive signal, connect the RF port as short as possible, as we did. And you can also put now some text. This is done with this text box. Draw text items or draw text box items. So we can say, okay, we put here note. Sorry, popping up the window. Notes for layouting. We put dimension, or let's say board dimension. What do we say? 52 millimeters by 25 millimeters. Mounting 4 times M3, and we have layers 2 layer. We can put this bold to distinguish a bit and say Okay, take size 50. Yeah, and we can put the note here. Of course, it makes sense. Sense to change a bit on the left side, and yeah, so we can put these notes, for example, here above our sheet documentation. So this would be things you should have, or you should do before now you can start with the actual layouting process. Now it's time to enter the layout constraints into KiCad. As mentioned before, we have in general two constraints. One are coming from your project, so the board size, how it's mounted, how many copper layers, etc. And the other constraints are coming from the manufacturers. So this means your PCB manufacturer will tell you what the mechanical constraints like minimum hole size, minimum track width, clearance between tracks and solder pastes, etc. And the base material manufacturer, which will tell you what are the physical properties of your base material and then resulting in the physical properties of the PCB manufacturer. In our case, in our Spring pre-class for the master classes in our international study program, we work with the PCB manufacturer LayoutEditor. He will tell us what are the strengths we have to sustain, and with the base material manufacturer Isola, who provides us the base materials for our PCBs. To start the layout editor, you have two ways in principally. First, you can go to the workspace manager and press the PCB editor button, or directly out of your schematic editor, pushing here on the PCB editor button. Once you have done this, the first thing you should do is to press the board setup, and we enter now our PCB constraints. The first thing which we are going to do is talk about the physical setup. So which copper layers do you take, which pre-breaks, and which cores. Then we talk about the board editor levels, so what kind of signals we route on which level of the board. Then we talk about the PCB constraints. These are the mechanical constraints from production mainly. Then we talk about solder mask and paste. What are the distance between the paste and tracks, for example. And then we show how you define different net classes, make it able to predefine some track width and layout constraints, for example, for power signal routing or for signal routing for intercommunication between integrated circuits. So let's start with the physical layer. If you see, we have the manufacturer constraints. Either you get them from the manufacturer's website, go to, for example, LayoutEditor, or you contact your manufacturer for any specification. And I cannot say it enough or pronounce it enough. Please do this before you start any layouting, because what you enter now in your PCB stack up and in the constraints of your traces and holes will mainly dominate the manufacturability of your boards. We assume here a board thickness of 1.6 millimeters, which is more or less a standard board thickness for two-layer boards. We take our project constraints, as we mentioned before, I don't repeat them again, and then we look in the board setup and click on the physical stack up, and here you start. We can select how many copper layers we will take, so we'll take 2, and then you see here the setup. F stands for front or top, and B stands for bottom side. Then you see here the core material, FR4 is a kind of PCB material. If you follow our class, we will have some presentations about PCB material from Isola. We will make a presentation at our university, and we will also have a presentation of LayoutEditor talking about PCB manufacturing if you follow our class in our international master. So here you can get, you will get information about what's called FR4. And then we see copper solder mask, solder paste, silk screen, so the different layers stacking up, and also you can specify here the thickness of the different layers, which in result then gives you the overall board thickness. Good, and now let's check for Isola Eleconta. We use the base material Isola 400. You see here on the left side the base material core, which means here you have a core, some pre-break and some added copper foil, red. Then we see that we have different pre-breaks. If you want to make a step up higher than 2 layers, you need then on the copper another pre-break before you put another copper foil. So you will see we have different pre-breaks. What's the difference is, you see this is fiber, is the woven is different, and will give you different electrical properties and mechanical properties of your PCB. All of this we cover in the presentations of Isola in Eleconta in our pre-class. Further, you see the thickness of copper foil and galvanic copper. It's going to be 45 micrometer, and also the solder resist is going to be 25 micrometer. And based on this material sheet, for example, you can calculate the thickness of your PCB stack later on. Good. So we have talked about the physical stack up of your board. Now let's talk about the board editor layers. Here you can give them different names or IDs, that's fine. And most important, what's very handy is if you say, for example, on the copper, on the front side, we route the signal, that's why we call it signal layer. And on the bottom side, in our case, it's a power plane, so where we route our ground, or the complete bottom plane should be ground. So we select here for the bottom copper power plane. If you have, for instance, for example, 4-layer stack up, then you would make signal, power, ground, signal. In this case, the front would be signal, then the first inner layer would be positive power supply, or no, the first layer would be ground, then positive power supply, and then signal again. So this is somehow how you can already assign different layer, different properties or signals which have been routed there. Then we come to the design constraints in the board setup menu. Now we see here the typical settings we need. For example, minimum track width, minimum clearance between tracks, minimum annular width, minimum via diameter, copper to hole clearance, copper to edge clearance. And this copper constraints, for example, can be taken out of the Eleconta data sheet again. You see here manufacturer constraints for outer layer and galvanic inner copper. These are the height of the different copper planes you can use. So for example, 12 micrometers, 18 micrometers, or 35 micrometers. And then you see here the pad, track distance, which you have to hold. And also you can see here the track width, the minimum track width, which is possible depending on the selected copper thickness. And if you see, the thicker the copper it gets, the higher the distance between, between different elements must be held, and also the track width increases. Why this is the case, we discuss again in our pre-class. Good. So these are the constraints. Then we have for the drills constraints, depending on the PCB thickness, you will be allowed to have different hole, minimum hole diameters. And this is so based called on the aspect ratio of 1/8, and then you can have 1/8 of the PCB thickness gives you the minimum hole millimeter, minimum hole size. Good, so this is also based information you get from your manufacturer. And the last thing we have to discuss in terms of producibility is the solder mask paste. Here you can select, for example, the minimum distance between pad and tracks, minimum solder mask web, distance pad, and clearance of solder mask and stuff. So you here can get all this information of your data sheet and put it into KiCad. The information given from the manufacturer sometimes is more than which you can enter into KiCad. That's also a reason why maybe you have to talk with your manufacturer or carefully check which constraints you enter now from your manufacturer data or manufacturer constraints into KiCad in order to get the correct boards. Good, the last thing is constraints in KiCad regarding the net classes. This is a help or assistance from KiCad. In order you can define already net classes to say, okay, the clearance is 0.2 millimeters in all cases, but the track width, for example, is default 0.3 millimeters. And if you use a power net, or you say, okay, this is a power net, the minimum width you can take is 0.5 millimeters. Like this, if you have bigger boards with different net classes, for example, high-speed signals, low-speed signal, power and high power, then you can define here already based on your calculations what should be the ohmic resistance of your trace at the end, approximately the width you meet minimal to route the signal. You can predefine these classes here in KiCad. Now we enter the mechanical aspects into our board. So what we draw in our layout editor is the outline of the board, here gray. To do this, we have to select edge cuts and board outline dimension at the rectangle. And then we place the mounting holes, the M3. They should be always in the corner 5 by 5. So from the corner, it should be away the center of your drill 5 by 5 millimeters. And another important thing is that we set our reference points for the grid and for the devices, for the footprints. And we will also add again the vision and designer information of your board in the PCB editor worksheet. Now to alter our mechanical dimensions, we select the edge cut, we select rectangular, and we know it's going to be 52 by 25 millimeters. What's very useful is that you can change here the grid size. Okay, so as 1 millimeter makes sense since our dimensions are in millimeters. You can have also grid in 5 millimeters or in inches, in mils, micro inches, since the typical spacing in the two-hole technology is going to be 100 mils. This corresponds to 2.54 millimeters. It makes sense during your layout that you change the grid according to the common component you want to place in your PCB. But drawing the outline, we do it with the 1 millimeter grid. Okay, so we have selected rectangle, we have selected edge cut. So let's start. You see here, we need 52, 64, 52, and now we go down to 25. So now these are our outline dimensions, so we click and it's done. Now, before we start over, we set the reference points. This is done here. If you click left and hold, you can select now the place the origin point for the grid. It's going to be here, left corner. And we also place the reference point for the component placement and drills. Put it on the same way, so we have it in the same area. This makes sense since then we know later on when you have a position which drill is done, if it's inside your board or outside, and one on the left, one on the right, one at the top, at the bottom, if you look at the Gerber files later on. Good. Now we fit to screen. We have our complete nice outline, and now we enter our M3 mounting holes. Go to add a footprint. Of course this, yeah. And then we put here M3, and now we put mounting hole, mounting, wait, N is missing, mounting, then we get here mounting M2, M3, M2. Can put also mounting M3. I think then we get a reduced overview exactly. Can put it like a dynorm, and we take this. Okay. So now the question is, how do we get this 5 by 5? For this is very interesting. If you hit the space bar, you can move relative grid. So if you look down here, you see dx, dy. Turn it off here. You see dx and dy on your screen. And for example, if we say we set the upper left corner, we go in the corner, and now we put space bar, dx and dy gets 0. And now we can go 5 millimeters to the right and 5 millimeters down, and we are at 5, and we can place our mounting hole. So again, for 4, 5, 5, mounting hole 1. Then we change our relative grid here. Spacebar gets 0. Mounting hole. So we see it's 5, 5, mounting hole 2. And like this, you can finish your mounting hole positioning. So the last thing we have to do is now to enter the data of the designer. It's the same, issue date is today, revision version 01, title any timer anyhow, it's any 555. Let's clear this timer module. We call it blinking LED, and the order is me. The order we put in the second, and here we put the company. Well, that's our outlined mounting hole for our PCB. Now, in order to place the components, we click here on Update PCB with changes made with the schematic. And then you can select some properties. We may just update PCB. And then you have to click close. And then when you move your mouse, you have all the components on your mouse tip. And we just move a little bit out of, and we put it in the middle of our PCB to see that more or less all components are fitting into this PCB. Now everything is prepared to do the routing. As we have imported the netlist, we see our schematic like on the left, the outline and all components somehow put inside. What we see are now the so-called fly lines or fly wires. These are the it's the blue lines or it's the purple lines which connect logically the footprints belonging to one net. So for example, here we see the capacitor, the charging and discharging capacitor, and we see that one part should be connected here somehow, another pin should be connected here and here. And so what we have to do is to resolve all these fly lines and then pour the traces. Obviously, these components are only grouped by resistor, diodes and other things. So we have to resolve and order these components or footprints. What we have to keep in mind is the layouting constraints. We have two copper layers. Top layer is signal routing, bottom layer is ground plane. What does it mean? To keep in mind that the bottom plane is ground, so we don't have to care about the ground pins, right? Because the ground pins, if you think it's a through-hole technology, the ground pins are always connected at the bottom side. So we only have to search or to resolve the crossings or the fly lines for the signal pins. So that's what we do. We solve all crossing of the fly lines or fly wires. And we can, of course, change the order of components. What does it mean? It means instead of resistance in front of a light emitting diode, you can also make a light emitting diode in front of a resistance. Electrically, it's the same, but it might help you to improve or to facilitate to make your routing more easy. So in order to do all this, we do the following. First of all, we look at our schematic. And we see, first of all, that the symbol in our schematic doesn't have the pinning like our footprint. If you look here, we have pin 8, then 2, 5, 4, 1, 6, 7, 3. And if you do the same in our package or our footprint, we see that we have 1, 2, 3, 4, 5, 6, 7, 8. So this means the footprint we have here doesn't follow the order in our schematic. What's clear, because the schematic is only a logical representation of our circuit, and now we go to realize a physical representation, so we have to take care about the footprint and the pins here. So what we see is, for example, output pin 3 is here on the left side of our package, and this is maybe very easy to start with because we have at the output only our light emitting diode and then our resistor towards ground. So what we have to take care is to route, to put somehow here the resistor, for instance, and the diode, and then we can route directly from pin 3 to the diode and then to the resistor, and the resistor is connected by the ground plane later on. So that's one possibility to say, okay, here we put our output circuit, then we have our charging discharging circuit, so this is R2, R3 and the capacitor in one line, and they are connected to pin 7. So pin 7 is going to be on the right side of our package. We see here pin 7, so it makes sense to maybe put this charging discharging circuit on the right side of our PCB board. So and then we have ground on pin 1. So this is going to be somewhere here, always just connected to ground, no problem. And pin 8 is our power supply, VCC, we see here. And here remember we have in mind that we have for the power supply some stabilizing capacitors and the LED indicating power is connected. So this baby makes sense to place these components here at the top of your package of IC. So what we did now, based on the footprint, we organized a little bit where to put the components on the PCB. Of course, theoretically you can put the output LED and resistor on the right side of your IC package, but it doesn't really make sense because then you have to move somehow from one side of the other side of the PCB. For this, for instance, you maybe can turn already your package, but the easiest is to see where are the pins and which circuitry to which pin, which is the circuitry connected to the pin, and then make a little bit rough floor plan where to put your components. So what we have seen, what makes sense is left side output circuit, right side timing determining circuit, so R2, R3, C2 on this side, and at the top side our power circuits. So now let's do this, and we start with the output circuit on the left side to route D2 and R4. So as explained, we now move out the footprints out of the area of our board and start to position the footprints, and starting with the footprint of our active device about our NE555 tunnel. So we zoom a little bit out to have another overview. left click, hold left click to mark our components, press M to move it upwards, and have now the selection. Now we select our NE555 timer, press M to move it, and we can move it a little bit, not in the center of our board, but a little bit to the left, since we know that on the right side we have our timing circuit, which might be a little bit more complex than our output circuit, which is only consisting of the LED and the resistor. Good. So then we can use, we have to identify the fly line somehow. On pin 3, if we remember, is our output. So this is an output. And then we can check which component is coming. But the first is, we remember that the ground is on our bottom plane. And we don't have to care about the ground connections because all through-hole devices are connected at the bottom to ground. That's why we can remove the fly lines for ground. And if we zoom in for pin 1, we see this is ground. And this is a ground fly line then. So if we right click now, and we see here net inspection tools, we can say hide net in rat's nest. And then the fly line is gone. Pay attention, fly line is gone. So we don't care now about any ground fly lines anymore, which makes the overview better. Now we can go to pin 3, output. We right click, we go again to net inspection tools, and now we say highlight net. So we see the highlighted net of our output net, and what we see is it's going to our test pin, going to our diode, and then from the diode, from this obviously to a resistor. So what we move now is our test pin on this side, our diode on the side. You can see we can at first put the diode and then the test pin. We are free to do what we want at this point. So maybe the diode on the very side is nice, and then we go to the other side of the diode and say here highlight net, and this should now, this is the other one side. I'm a little bit curious. Now we should now get a fly line to the resistor, but we don't. Here this is net. Maybe no, there's something wrong. This should get to show net, and then net inspection to highlight net. Yeah, this is our resistor. Select, press M to move the resistor, and then we can put the resistor maybe at the bottom side. So now if we move in, we see it's a little bit dense, right? But we can move now, we keep the resistor here. Test point here. Move the diode. We let the diode out between the two mounting holes. I think it's nice to see there the diodes lightning. And then we have here the output connection, and then the resistor, and we move for test purposes. Print test point. Sorry, move the test point. In the middle. Good. So now we see we can route from pin 3 to the test point, to the diode, and then to the resistor, and then to ground. Good. So, and this we do this also for the outside, for the timing circuit. For this, we know that we have to go to here, to the ground VDC out, pin 7. So we have maybe to see what's on pin 7 and 8. So what we want to route now is pin 7 exactly. We can also take here, highlight net here, example, so. And if you close now, we see also highlighting here. So what we have to move, of course, is our diode, our resistor, and then also our capacitor. So we take complete component and as I said, the aim is now to put all the components in a way that we have no crossing the flylines anymore, since the flylines are the paths which we later fill out with copper for the traces. So if we have placed all components and removed all crossing in the flylines, we get more or less this picture. As an example, your picture can be seen differently, it can look different, but this is what I get. So check, for example, pin 7, which, if you remember correctly, is here this net going on the diode, and later the net pin number 6, the charging and discharging way, in order to see if we have any crossings. Let's do it here. We highlight the net connected to pin number 6, our charging discharging current. If we go to the layout, we see here we don't, from pin 6 now, here we don't have any crossing. We can directly put a trace, but from 2 to 6 we have crossing with the VDC here, pin 4 and 8. This is the only crossing left in the complete board which we still have to resolve. Okay, this is one thing we have to do. I want to show. Now we turn off the highlighting, so right click in net inspection tool, clear highlights. What we also have to do is to get rid of this gray text, because this is fabrication text annotations for the fab, which is not printed on the board, so it's only for information later on. And turn it off by layers, fab, front side fab, and we left click on the eye and we see it's gone. So what we see now in yellow is the silkscreen printing. So this is printed on your board during manufacturing. If we go up, front silkscreen, we turn it off, you see these are the printings. And they should be at least inside of your board. So this one, C1, have to be moved, for example, to the bottom. Then we move maybe this to the right in order not to get confused. Honestly, the reference for the mounting holes we can delete. Select enter, select delete, select delete, select delete. And here we see R2, and this is overlapping, might cause error later on. We select move and we can move the labeling of the devices a bit so that it's clear to what the labeling is belonging to and not overlapping. The other thing, you have to check that these courtyards are not overlapping right here. Good, this looks so far fine. Another thing we can do is to check with the 3D view if everything can be soldered and accessed. This is 3D view. We see if we have now here our screws, that's fine. Here's our power supply. This is just connected. That's fine. You put it with the connector. Test points here. This can be also accessed. If you think about, you can come from here with the clamping. You can come here with clamping. Here for this test point, this one is a little bit located not so nice between the two LEDs because you cannot contact it easily. This would be more handy if this test point, for example, would be here. This is something we can change at our design. Close our 3D view and we move this test point between the screws. The screws might be also not so high, and like this you can easily contact test point 1. We save, we check again the 3D view, and we see now, so this can be connected easily, the test point 1. We can even move it a little bit further out, but I think it's fine like this. Okay. So this is how our circuit is now looking like. Now, having been so far, after the components are placed, we have to question us, is assembly possible? So if the components are to stick too much together, but I think this is possible even with the hand solder. You have to think about, of course, in which order you're going to solder. Maybe solder the small, not so high components first. This might be, for example, all resistance values, then the socket or the IC, then maybe the capacitors, then the test points, and then the diodes. It would be one order. But the thing you have to think about in the order of soldering, which is practicable and which is practical good and what is not so easy to solder. Check the axis of the test points. This we just discussed. Since we have here the screws, we can access this test point very easily, and here too, between the two screws we can access the test point also very easily. That's fine. Make sure you can read all texts in landscape and 90 degrees turn. So in landscape we can read R1, TP1 exactly, and if we turn clockwise we can read R3, D3 and D2 and J1, but we don't have to turn counterclockwise, so that's fine also. So the next step would be to pour the ground plane and see how the ground connection, this is poured, and we then need only to resolve the traces. Now let's pour the ground plane. In order to do this, we select the bottom copper because it's a ground plane, the bottom, and we use here this add a fill zone area. So we start with fill zone area. Here we have, you see now we have a grid problem. You see, because we are in mils, so it's not a round numbers of millimeters. We know that we have used the millimeter grid, so take millimeter grids, and now we match exactly. Then at the first point you have to select what net this should be, and of course we say it's our ground net. So then we put ground, and here left click, and then we have selected the area. Save. What you can do now is you can right click on zones and you say okay, fill all zones, and then you will see how it's looking when it's produced or when it's filled. And what we can see now is that the ground pin is connected to ground, and on the top you still have to route the fly lines. And we see that this component is here. You see that from the edge of the board to the cover plane we need some distance. This doesn't matter, this component is a little bit overstanding. Can move it a little bit inwards, but it's not so much, it's not so troubling. But this looks quite nice. Good, if we have filled now, we have to think about how to continue, and especially how to resolve our crossing here. Okay, what we are seeing now is our board, how we just stopped in our layout editor. And what we take with us, or the problem we want to resolve, is the crossing here. So in principle, you have different strategies to resolve crossings. First is you can route between pins. This means if the width of this trace can be small, you can go between two pins of a device. You can do it. I try to avoid it. You can route under components as a second point. This means, for example, you can go under R3 or the diode D3 because the distance between these two pads or the through hole is quite large. Or as a third possibility, if possible, you can route the power supply also on the bottom layer. So if we check, we need to connect pin 8 and 4 together, the VDC pins. And if you think now we route this on the bottom side, we have really no problem because we have only one slice in the bottom plane and all other ground pins are still have a low ohmic resistance to our ground pin at the bottom side of our board. So that's not really an issue to make this routing on the bottom side, but that's what we're going to do in this case. And then we have to connect pin 2 and 6 together, and this we can do on the front side. So we have connected these two pins. We have resolved the crossing. Also in terms of crosstalk or capacitive coupling, if you think you route one here and one here, the area where the two traces are crossing and which are giving possibilities crosstalk is minimized because it's more or less a 90-degree section. Okay, if we have resolved this crossing, we continue to do all the signal routing. So connecting on the front copper all our flywires with traces so that the flywires are gone. And then we pour our ground plate on the front side with copper. As I said, if you think you only have traces for these fly lines here, there's a huge amount of copper which have to be etched away. And this means your etching liquid is saturating early, producing coats. That's why you avoid it. And you pour copper and only slice the copper where you have the traces. That's the one thing. And electrically, it's nice to have the copper everywhere because you can have shielding for the signals around you. Okay, let's go and finish our PCB. As said, let's start with the resolving of the crossing here of the connection from pin 4 to 8 of VDC and pin 2 to 6. We go to the bottom, we select root trace, we click on pin 4, we go to pin 8, and now it's connected. Unfortunately, now we have a shortcut between VDC and the ground plane. To resolve this, we right click on the bottom port area and we take here zones, fill all zones, and now the ground plane gets sliced and we don't have a shortcut between VDC and ground anymore. In order now to route all the traces on the front copper, we select the front copper and then we use the traces, and now we can select all the pins and fill the resolve all the fly wires as I do now. And here we see one VDC which we somehow have to connect, but this is no problem since we can connect it this way, and nobody, you see we have here a crossing, right? But nobody forbids us to go VDC in this way. So now we have connected all flywires. At least I don't see any flywires anymore. And then if we have done this, we can also pour now our fill zone on the top, on the front cover. So we select front cover, add a fill zone, left click on the upper left corner, and we say ground. Okay, then we mark our PCB completely. And we have our fill zone. Marked, now we fill the fill zone somewhere on the filled area, right click, on the filled area, right click, zones, fill all zones. And now we see how the top layer is also filled with copper. And so far our board is finished. We save in order to store. Now we are finished with our routing, and we have to discuss to proceed now with the checks in order to check if we have errors. So the design rule check is going to be performed, and later on to export the Gerber files. One thing I want to discuss before we continue with this project is freestanding islands of copper. So if we look at this layout of our circuit, the same task, we want to lay out our NE555 timer, but a different realization. Also, we performed here bottom plane is ground. We have our pin 6.2 in this case connected on the top plane. And what we get here when we pour now our copper on the top plane, we got such an island. It's called an island because it's not connected to any ground plane, and that's not good. We want to have connections to ground planes in order to have some shielding, EMC improvement, and so on, and of course save money by not etching all the copper away. So what you can do is you can use freestanding vias. So you select vias in your menu and you can place them where you want. For example, here you can add vias between these ground planes. So you have the top ground plane and the bottom ground plane connected at several points, on several points together. And this makes it very low ohmic if you make this additional connectors here. And this is also the way how you can fill this. So you put freestanding vias here, 1, 2, 3, and then you fill again the ground plane, and then this area will also be filled with the ground plane because you have these wires here. So keep this in mind once you make your own circuits and you have these islands here. If you put here some wires and you pour again your pouring area, filling area, fill zone, then you get here also copper, and you have the shielding and coast saving in not etching this away. Now we are ready for production, and we have to prepare our board for production. What does it mean? First, add project information on the silk layer. If we see now our board and we get to our manufacturer, and especially in our lab case where we have maybe 12 groups or 16 groups, we will get back 16 of these boards, and then everybody can look at the boards and find his or her board. Maybe the board has been designed 4 weeks ago and you don't know how your board is really looking like anymore. So that's why we are going to add some project information on the silk screen, and then we perform the DRC, so the design rule check, if we have taken care about all constraints for manufacturing of our board. So now let's start to add some information on the silk screen. So if you look here, maybe it's easy or it's good idea to put it somewhere here, your information, and we move C2 somewhere here, and then we can use this area to write some text. So we go to front silk screen, so this is this. We can select C2, move it here, it's clear this even here, so. And then we can use our add text item, and then we put group A name and student number, let's say 0, 0, 0, 0, 0, 0, 07, 0, 0, 0, 7, okay. It's a little bit large, we rotate it, we mark it here, and then we say all arrow properties. Hopefully we can change the text size. Somehow. We should be able to change the text size. Area. Also. No. Undo. Control Z. Properties. So we take 0.5. Yeah, this is the size of the width and the length of a character, and we just put it here, which is nicely on your silk screen now. So we put information on the silk screen, and then we perform the design rule check. This is this button here, show the design rule checker window. We open up, redefine all students before performing design rule check. This is good. And then we run DRC. So we have no errors, only 2 warnings. And take the thickness of our thickness out of range of our text. Okay, minimum height, yes. So this is something we say okay, keep it like this. This is a risk we take. If you maybe so that's fine, and we can go to production with this board. Once our board is ready for Gerber file export, you have to plot these files. So this means you go to File, Plot, and this menu pops up, and you have, in order to plot the Gerber files, to plot the right file format. In our case it's Gerber. You have to choose the correct directory, of course, and the general options you leave like they are, and you have to check that you use the extended X2 format, which is recommended. Then you plot first the Gerber files and then generate drill files, because the hole positions and stuff and hole diameters which have to be drilled are not included in the Gerber X plot. So that's why you have to do these 2 steps, one after the other. One big information about, one very important information for our students from Hochschule Darmstadt, University of Applied Science. You will get information in your course which data you have to export, and check out the Moodle course for a checklist what in which format you have to submit to us in order to get to PCB manufacturing. Last but not least, once we are done with the Gerber file generation, we will check our Gerber files. For this we do go to the KiCad project manager and we start the Gerber viewer, and here we can check the generated files. So as said, we have to go to File, plot. We have here our Gerber file selected. We have the extended 2 format selected. We have to go to our projects. Yes, project finished. We make a folder here. Gerber. There we put the Gerber files. Select folder. Yes. And then we say plot. Warning. Warning. With correction constraint, the width correction value must be in the range. Okay. Can use this generate print files. The output folder Epsilon, you just keep it like this if you don't get any other information. Done. Close. Close. Now we have done this. Save part, and we open up the KiCad project manager. Open the Gerber viewer. And here we can file. Open auto detect files. This is the easiest way you can do. All. Okay. So then he shows you the Gerber files, you see. And now you can select and deselect the different stuff. First deselect all. So then we say for layout finished, non-plated through holes, other drills. So these are the big issues. The mounting holes, other drills that have plated through hole. That means that these connections have inside a galvanic copper surface. And here you see our components values, the drill files. Then the bottom cover. And maybe, I don't know, yeah. Like if you use the blue arrow, you can set it on the drill files, and then you have the background, our copper, and then you see where are the drill holes, and if they are, for example, you can see if at the package of your IC, if there are all 8 drill holes are in the center of the copper, and so on. Okay, silk screen is for the bottom is not so interesting. Let's go to the front mask here, front copper layer 1. For this we turn off maybe the bottom layer, and then we see the front copper layer looks also nice. And then we can put the silk layer for the top, F, silk screen. And we see the silk screen. So you see it's nicely produced. And we can put all that on the edge cutout, and then you see the cutout of the PCB is larger than our files. And if you put here all the revision number and stuff, you can be sure that what you generated in KiCad in here is the same revision. Okay, that's all about the KiCad Gerber generation, drill file generation, and Gerber viewer. Now let's talk about the exercise for you. Your exercise is now to enter our circuit, which I just showed you, on your own into KiCad. Use the same PCB constraints, 2-layer board, M3 screws, signal routing, ground plane, and VCC for the bottom layer. Update your schematic, insert test points, and make a new version of your worksheet. So that's the exercise you should do based on this training. Yeah, engineering best practice. Ask yourself and your team question how to test, how to mount, how to assemble. This is essential in the step before you go to the PCB layouting. Update your schematic in the way that you take into account these points. Before you start to layer, print out the main circuit, print out the main component footprints, make a rough planning where you place the different sub-circuits. That's what I showed you. For example, you think your central core unit in the middle of the PCB and surround the additional resistors, capacitors, input-output circuitry or power supply circuitry accordingly to the pinout of your main circuit to make it the tracing or the routing not necessarily complicated. Into the mechanical aspects first, edge cutout, mounting hose, place the connectors, because these devices are mechanical devices, so they have to be at the position where you need them in order to use it in your application. For instance, if in a car you make an electronic control unit, the connector is on the left side of the engine, so it must be on the right side of your PCB, for example. So stuff like this has to be taken into account. This is the first you do, because otherwise it doesn't work. Put the project information or silk screen, project name, version, author, date, in our case group number and term. Run the DRC before you export it. Export Gerber and drill files. As mentioned, you have to do this in 2 steps. First the cutouts or the areas, and secondly the positions of the holes. And last but not least, always check with the Gerber viewer before you go to manufacturing. What's possible? You see here nicely single board computer. Run Linux and Android. The design is based on a 4064-bit ARM CPU, includes 1 or 2 GB DDR RAM, 4 GB flash memory, micro SD card socket, Wi-Fi, Bluetooth Low Energy 4.0, Ethernet, HDMI, audio and video. So this is really advanced board, and all this can be done with KiCad. And I think this is quite amazing, and you see what power this layout tool is bringing with you. Good. Last but not least, thank you for watching the KiCad training. I hope you have fun with your PCB design. I hope you enjoyed this training. Take care and see you. Bye bye.